So and hide this. Hey. Oh, this isn't homework 10. Sorry. Yeah. Thinking 10. That's why it's missing some things. I have more too to add. I have 2 more books to add here, but they won't help. The second book will help because he gives a nice description of Raman and Brilliant scattering. But he doesn't give the equations. None of the books give those equations. They give a lot of equations. They don't give those equations. But in that book, I can't seem to get that book. At least not. I haven't actually looked in the library, but it's probably in the library. I don't know why this clathrate thing is here. It's just stuck there. And this is this book that's supposed to have the answers. This is the spectra for propylene glycol. It's useful, I guess. And then I guess I should open up the heat capacity slides. And at the bottom somewhere here. All right, so the homework is the main thing here today. And again, I'm not going to have a good answer. So this guy, one of these is a book, right? So you have to go to the end. Math should show up. But this book isn't. This book is kind of the same subject. The chapter, I think it's chapter 1 or something. I have a better, kind of a better book. Let's see. 2 is the thing, resonance phenomenon. This thing is improving scattering 69. So that's in here. So you can see there's a lot of math involved in this stuff. It looks like you could read this. Some things you just have to like let it soak in for a long time, like 20 years. Then maybe you can start to figure out what's going on. And I think Brilliant scattering seems to be one of those things. Yeah. So there's a
years for the next homework.
Yeah. So it's like basically there's a superficial level of understanding, which is more than enough, right? Even if you know the word is pretty good. But and then there's like this goes on and on and on. So, and the thing is, I have 3 books. I only have one of them posted. I'm going to post the other 2. But basically, each one of them gives a different. It's as if they're speaking a different language, or talking about a different thing. Yeah. So, and none of them have the stuff like what this guy says, which is supposed to be the 100-year anniversary issue, which is supposed to be so simple, right? Like this equation. Where did he get that? That's one of the homework questions. You can't exactly find it in a book. ChatGPT won't answer it. You know, in a wiki search or something is pretty hopeless. So some of the things are pretty simple. Anyway, you can make a hit at it, you know, like you can make a hit at that equation, and then it's like 5 and 6. That's about you kind of make a hit and try to make some kind of logical discussion about it. So 5 you can kind of figure out, and 6 is harder. I think maybe it's 4 and 5, I guess. Yeah, 4 and 5. 4 is easy. I mean, easy for me, and 5 is harder. And then that 2 is like, I don't really exactly know where that came from, but I can kind of make some kind of argument that there could be 2 terms here, you know, if you look at it the right way. So Anyway, so the first thing, so this is about brilliant scattering. So again, like a week from today, so we can at 3 o'clock, we can go down and look at Nichols' brilliant scattering machine, which I don't know, you can bring beer and chips if you want, you know, it's like, gonna be pretty exciting, you know. Basically, he's gonna run some sample too, so we can see the spectrum, which is good. So it's almost like a lab. But unfortunately, it's after the homework is due on Monday, or Monday is still not a holiday, right? So I can have a homework due on Monday. You guys can beg off, but let's leave it at Monday. It'll be good. Then
I don't think we have class next week.
no, we don't have class on Tuesday. We have class Thursday, right?
Tuesday is, I think, reading day, and Thursday is Veterans Day.
Friday's Veterans Day. Yeah.
It's technically Saturday, but it's observed on Friday. But in the UC calendar is on Thursday. Should be Friday.
Yeah, I think it's Friday. According to the undergrads and the other classes, Friday. They seem to know what's going on. I mean, I didn't even know, like it always sneaks up on me that November 11th thing. That is a pretty good movie, that All Quiet on the Western Front. Like, if you, yeah, it's kind of really, and everyone dies, like literally everyone dies at the end. The war is over, yeah, and then everyone dies. The general's like, oh no, we have to go back home victors, even though 10 minutes left in the war, and they all go out and get killed. And the hero of the thing, the guy you think he's definitely gonna live, gets like knifed, you know, just for no reason, just pointlessly. Oh, he kills someone first, and then someone kills him. But anyway, it's still a pretty interesting view of like, especially because they just came out that the Ukraine general said we've lost the whatever they were going to do. Like they had their thrust, you know, to whatever, take over, reclaim, whatever. And then he said like it's just like World War One. So it's kind of appropriate. He says on November 11th. You know? It's like anyway. So yeah, this thing. Right. So some of it's not that bad, I guess. Figure 2 shows a raw data. So you got, so this is the output of a Fabry-Perot interferometer, which is, that's the popular one. So that's, so that if you look, all right, so you can Google interferometer. The first one was this Michelson interferometer, which is like this with the mirrors, and one of the mirrors moves and they recombine, right? Someplace is a list of all the interferometers. This isn't it though. How about types? I did this yesterday, so it's definitely a web page list of types of interferometers. There's a lot. I mean, all of them are going to be like a wave splits into something and then recombines, and you get an interference pattern by how you move the whatever, right? But so the Michelson is the one with the mirrors, right? That's the thing I kind of described. That's probably, I think that's the first interferometer. And then these are using these Pico, whatever.
The same concept used to detect gravitational wave.
Used to detect what?
This concept was used to detect gravitational wave.
Oh, right. Yeah, yeah. That's right. Yeah. Anyway, Fabry-Perot. Guess I should remember that. I call it Pico, but it's Perot. It's funny I can't pronounce the French names like Brouillon and Perot. But anyway, there you go. All right, so it's using kind of lenses with the angle of the lens is really small, and then the light, it's the same thing, recombine all the waves, and here you get an interference pattern. Right? So it's kind of similar to the other interferometer, and you have interference and you're measuring it. And if it's monochromatic, you get these sharp spikes from it. And if it's got a spectrum, then a spectrum will appear in that. And then before you transform that to get the pattern. So you're going to do a slice through this with a CCD or something, kind of So you see, like, you're gonna do a slice through that, so you have this repeating thing, and the distance between those repeats is that the distance that the wave traveled is one wavelength of the light, so that it repeats the interference. So it's reached constructive interference because it's traveled one wavelength. It goes constructive, constructive, constructive. So you're gonna get a series of peaks from that thing. That's what he's got. So the pattern he's got is here, right? And then the wavelength of light that he's using to measure the spectrum is that distance between those peaks. And normally you wouldn't show three of these. In one of these books, I'll post those books under the same homework thing, but I didn't have time to do it. But they show a case where they can cover the entire frequency range up to Raman. So Raman's going to be like way over here. So they, in other words, they have a wavelength where they have a gap big enough that they can measure both Brillion and Raman. So they show a pattern where they get both with one instrument. So you can see that this peak's near the peak. So this is the main peak, is the constructive interference for the main beam, like the incident radiation. So that's the elastic, kind of like the elastic peak. That's elastic scattering. That's the elastic scattering peak. And then every time your mirror or whatever you're bouncing through the lenses goes through one wavelength, you get a duplication of the same thing over and over and over again. And you can go forward and backward with that. So that's why they have these repeat patterns in it. Right. So the spectrum's in the middle. In fact, the spectrum is just like, well, it's a part, you have the Stokes and anti-Stokes. You have like gained energy and lost energy. So normally you'd expect the Stokes to be larger, like it's easier to lose energy than gain energy from the vibration that happens. The anti-Stokes would be like temperature caused it to vibrate. That vibration from temperature is added to the light and made it shift the frequency higher. Right, so that's kind of the way this thing's going. Right, so raw data obtained from infrared displays explain the Rayleigh and Stokes in it. So that's basically, you're adding, like the vibration can take energy away from the light, or the vibration can add energy to the light. So if it adds, you're going to get a higher frequency. If it takes away, you're going to get a lower frequency. So Stokes is lower, anti-Stokes is higher. And it's getting the vibration energy somewhere else besides the light. So the light can excite the vibration, leads to Stokes, and you get a lower frequency for what comes out. Or the temperature can vibrate and it can add to the light, and you get anti-Stokes, it's higher frequency. Right. So in the case of Raman, that's vibrating a chemical bond. So it's like the bond's like a spring, and it's making the spring shake, and that's a high frequency one. In the case of Brillion, it's the lattice phonons that are doing it, and it's at a lower energy. So shaking a small bond takes a lot more energy than moving the atoms in a crystal, because smaller things are harder to move than larger things. The frequency is higher. Small bell has a higher pitch than a big bell, that kind of thing. So these are, so these are quantized transitions. So it's not the total energy that you put in to ring the small bells. It's the energy that it takes to ring one small bell, right? So it's, in other words, you could think like it's going to consume a lot more energy to ring a gigantic bell that's the size of the room than it is to ring a little teeny dinky bell, right? Pixie bell or whatever. So that's true, but basically there's the amplitude of the vibration, and there's the amplitude is the y-axis and the frequency is the x-axis, and they're both kind of energy. Like one is like the power you put in to do it, and the other one is like what kind of energy, it's what can the radiation do? Like sunlight will give you a sunburn, UV will give you skin cancer, X-rays give you bone cancer and blood cancer, because they can penetrate more. And you could have a small amplitude X-ray or gamma ray could cause a lot more damage than a huge amplitude visible light. Right? You could be in a solar tanning booth for hours and nothing would happen to you. You could just get a little dose of X-rays and you got blood cancer, leukemia. Right? So there's two things, like what can it do is the frequency. And that's an energy. And then how much is like the amplitude. There's two energies, energy, energy. So it's kind of confusing. Like you think like these little things are not going to take that much energy. They don't take that much energy. Like a radio wave for NMR, there's not much energy being transferred. But basically, anyway, so there's two kinds of energies. So it gets confusing because you have the what it can do energy, which is the quantized part, and then how much isn't quantized. So you can put in as much as you want. It's going to be put in steps of the quantized thing, but the amount isn't really limited, right? So anyway, so that's kind of what's going on here. So
we're still talking about the phonons, the collective vibration, right?
Yeah, that's the thing about frequency. Like, so different things happen at different frequencies. So if you're at this low frequency, you get a phonon, and then you take the same kind of radiation, electromagnetic, and you go to high frequency and you vibrate the bonds, and there's no sound involved, right? So sound and light kind of correspond, couple up in this kind of brilliant part. In other words, the vibration energy of the sound is the same as the energy of the radiation going in. Just like for NMR, the energy of a radio wave matches the energy it takes to take a nuclear magnetic spin and tilt it. That's a quantized energy. It's the protons or something are spinning around, and then basically it's got a moment of inertia to it. It's got a tilt to it. And the radio wave, which is like zero energy, just like can pop those things over. Right. So
we're still thinking in terms of lattices though, right?
If you have a crystal, yeah.
Okay.
So you can do, like he shows, all right, so that's a pretty good point. So this is the spectrum for propylene glycol liquid.
So
that's not a
different.
crystal. Yeah, it's a liquid. So what kind of vibrations you can get? So you can get longitudinal vibrations in a liquid, like a compression, like an accordion, but you can't get transverse because there's no shear. It can't withstand a shear stress. There's no transverse vibrations. And you can get longitudinal transverse optical or longitudinal transverse acoustic sound, and if it's sound, it's going to be at the really low frequency, and if it's optical, it's going to be at the really high frequency. But either one can be. You can have the different kind of shapes of either one, like the accordion type or the water wave type. There's only four things here. There's longitudinal, acoustic, optical. There's longitudinal, transverse, optical, and acoustic. So there's four types. And you can have longitudinal, transverse, optical. You can have longitudinal and transverse acoustic. Then that's it. That's all there are. But you can have different kinds of vibrations in a crystal because you have different lattices. Like the acoustic vibrations can be different. The same with the bonds. So the atoms are bonded together in the crystal so they can absorb energy like vibration, like IR, Raman stuff, atomic bond vibrations. So you can do these techniques with either a liquid or a, that's part of the question in here. Like, because he shows for when you have a transition between, down at the bottom, he's got a protein. So you can do it with metals, and that's where this technique was developed, but you can also apply the same thing to like drugs or whatever you want. So he's got acoustic, longitudinal acoustic for the crystalline. So the drugs like this paracetamol is like the standard thing that people look at for drugs because it crystallizes. Anyway, this is some other drug, indomethacin. I don't know what that is, but basically he mentions paracetamol in here too. So I think those are things that, like, I guess they think it doesn't really hurt you, so you can just mess around with it. But I mean, so he's got the crystalline one has a higher frequency than the amorphous one. In other words, it's kind of stiffer, I guess. And then, but the breadth of the peak, so the half width and half max, so the crystalline one is larger than the amorphous one. So it means this half width means something different than the peak height. He shows that here. Like here's his liquid polycrystal glass. So the glass has a sharp peak and the crystal has a broad peak. So the breadth of the peak and the position of the peak are two separate pieces of information for this thing. So that the frequency is the energy, and then the breadth has something to do with something else. And then the actual, I mean, the frequency is going to have to do with this, the modulus of the thing, and the breadth has to do with something else. So it seems like the more perfect it is, the broader the peak becomes. That's true also in so there's other dynamic techniques. In fact, Nichols does the other techniques. You can do the same trick with so this is with photons, right? And as you're coming in with light, and you can do the same trick with neutrons. So you can have a neutron come in, and then you can get Stokes and anti-Stokes loss in energy of a neutron interacting with a material. The neutron's interacting with the nucleus. So basically it's flying through all the electrons and just interacts with the nucleus. So that's kind of, you get the same kind of patterns from it. And all right, to do that measurement, you need a nuclear reactor. Like you have to have a nuclear reactor, you have to drill a hole in it. And you have to take the neutrons out through a hole and run it through a pipe. And then you can, it turns out neutrons will conduct through quartz, like solid quartz, without no loss, like a vacuum to it. So you can have quartz waveguides, and then look at the energy spectrum of the neutrons that come out. Because neutrons have mass, so the big ones move slower than the small ones for the same kind of temperature. So basically, if you have a like a helical tube, right, that spins at a certain speed, and so if you spin it really fast, the fast neutrons get through, but the slow ones don't. And as you change the speed of it, you can pick out the different energies of neutrons. So it's a velocity selector, they call it. It's kind of like interferometer for neutrons. All it is like a helical path of a boron filled. Boron absorbs neutrons, and it absorbs the anyway, they do the same thing with neutrons. There are ways to monochromate neutrons. Generally, like a nuclear reactor, it's not monochromatic, right? Because it's basically an explosion. So you can kind of monochromate with these velocity selectors, and you can do spectroscopy with neutrons if you want. Nichols does that. They do that at Oak Ridge, and they do that at NIST in Washington. So you have to have a nuclear reactor, or you can do, they call a spallation source, which is like take a particle beam, blast it in a piece of metal, and you get like mixed radiation out of it, right? So that's another way to, it's called a spallation source. You just blast a piece of metal with a huge energy particle beam, and all kinds of radiation comes off. And then they use this time of flight method to separate the different wavelengths and neutrons that fly off of that. There's other radiation too. And then basically your detector's timed on picosecond level. So you can separate the wavelengths. So you can get kind of monochromatic to your detector by timing the detection cycle. And the pulses, so you have an accelerator blasting a piece of metal at 60 hertz, right? And then, so you get like so 1/60th of a second pulses of neutrons coming off. When they fly down a tube, the tube has to be huge to do this. It has to be like, I don't know, football field long or something, half a football field.
You said this is in DC or Washington
The
State?
spallation is in Oak Ridge.
Oh.
Yeah.
I got lost.
The machine costs, all right, to build one of these is $1 billion. Literally, it's 500 million, but it's roughly $1 billion to build it after you put the equipment on it. The box itself is 500 million. And then the ancillary equipment and people and stuff hanging out is like another $500 million, about $1 billion. So that's what they do. Actually, it's right next, the one at Oak Ridge that they built for $1 billion is right next to the Y12 plant where they do enrichment of uranium. plutonium to make nuclear bomb fusel material, whatever. So it's like there's a fence. Yeah, there's kind of a fence there. I'm like, you don't want to get near the fence because guys in Jeeps will come up, you know. But anyway, there's a place to do this in Oak Ridge. You can do it. You can just write a proposal and say, I want to do the energy loss of whatever stuff I have and see what the spectrum is. And you get the same pattern you get from his Brilliant thing downstairs, except it would be like a neutron sensitive one. So if you deuterate, so if deuterium and hydrogen have opposite signals and things, so you can do things like tag your material with D and H and kind of other things. Nice thing about neutrons, they blast, like if you have a drive chain for a car and you want to do X-ray diffraction while it's running in the car, you can't do it because X-rays will only go about like 20 microns into the steel and that's it. They totally absorb. But neutrons can go directly like right through the drive chain because there's no absorption of neutrons because they don't interact with the electrons. There's not many nuclei. So say you can get a diffraction pattern from an actual drive chain while it's actually in a car. And you can do things like neutrons, if you use D2O, it's kind of invisible to neutrons. H2O absorbs a lot. So if you can fill your like fuel cell with D2O instead of H2O, then you can do like neutron imaging of a fuel cell while it's running, like track the hydrogen going through it. So a little bit of hydrogen in there will show up. So you can do things with a lot of like bulk scale things, but because there's not many neutrons that come out, so like you don't get a lot even from a big nuclear reactor. Like they have a 60 megawatt nuclear reactor at Oak Ridge, and a power reactor is like 120 megawatt. So it's a huge reactor. It's enough reactor to power like a small city, you know. And even with that, they don't get a lot of flux out of it. There's not a huge number compared to X-rays. X-rays, you can basically, like in a synchrotron, you can burn paper with a beam. You know, I've done it before. Even with the beam after it's gone through monochromators and been cleaned up, it's not the raw beam. It can still burn paper. But neutrons is not enough. You can stick your hand in it, nothing really will happen. They have a lot of safety, so you can't do that. But the problem with it is that the neutrons will activate. So when neutrons are absorbed, the way they're being absorbed is by adding neutrons to the nucleus of the atoms, right? When you add neutrons to a nucleus of an atom, it becomes radioactive. It's like if you have like gold, like a gold ring, that becomes active if it sticks into the beam. So an active means it gives off X-rays. So basically, all the gold in you, or metals in you, or iron, you can become iron 55, and then it decays after a while. But basically, anything in you that's metal is going to probably become activated by the beam, and then you're like walking radioactive, and you give yourself cancer from the inside out by the byproduct. The neutron itself doesn't do anything, but the activity it creates in the metals isn't good. Anyway, so there's a lot to that. But so Nichols does the stuff. We can ask him about that if you want. But so he does it on neutrons. So he's looking at membranes, like biomembranes on this. So he's using D2O and H2O to tag the things, and then look at how the water molecules like shake and bake when they go through a membrane. You know, so you can ask him. I mean, he's pretty interesting. He's a really bright guy. He's really smart. So, but you know, some of it is, he's at a pretty high level of stuff too. So, but anyway, he's also doing he's doing a lot of simulation stuff too. So it's kind of interesting to talk to him. But anyway, so this is about that kind of with the light scattering, Boolean stuff. So let's see. So there are people doing this kind of work, you know, and there is some research money in it, but it's kind of hard pressed to think like what company is going to hire you after you get a PhD doing Boolean scattering, you know. So it's a little bit of there's research money in it, and then it's of use for fundamental studies, especially about dynamics, and especially in biological systems. But even a pharmaceutical company where this stuff would be important, like you can see that they're pitching it to pharmaceutical when they're looking at like drugs, drug motion and drugs, you know, and then seeing what's the difference between a glass and a crystal drug. And there's a direct impact on the marketing of this stuff because the crystal one won't work and the glassy one does. because it dissolves. This one doesn't dissolve. So basically, if you have a pill, I guess you want to have glassy paracetamol. So, because the other one won't do anything, it'll just pass through you. So, so yeah, it comes down maybe to the mundane at some point, but right. So anyway, so figurative raw data, explain the Rayleigh-Stokes, should be able to do that. That you can kind of Google maybe. Why are no transverse peaks? He explains that in the paper. He gives one line that says like it's liquid. And then why are there 3 duplicate spectra? That's because the thing, so it's because you're going through one wavelength. So you're scanning the wavelengths. So these are shifts from an elastic peak, which is in the middle, and every time your interferometer goes one wavelength distance. So, I mean, if you think about it like the Michelson interferometer, you've moved your little plate like 0.6 microns. This is like red light, right? So you moved it. So yeah, like an inkjet printer can move 0.6 micron steps. The steps are going to be like less than 0.1 micron in an inkjet printer. So basically, you could use an inkjet printer to make one of these to get the motors out, stick mirrors on them or something. I had a reason I mentioned that. I had a grad student that did that. Like we were building an optical thing, and like he took apart a bunch of inkjet printers, and he put the whole thing together with inkjet printer motors, and he wired them to run it through LabVIEW or something to run the motors sequence, whatever. Anyway, it's possible to use pretty kind of useful to have old inkjet printers. Anyway, so you can step through it and get the side bands on this thing and then figure out. So that's going to be your pattern. Basically, it's going to be going down here. In order to use it, you're going to have to Fourier transform that. This has a sharp peak, so it's just one vibration he's looking at. So this polypropylene glycol, that's the Raman spectrum. I think this is linked in there, but so this page has all the spectra. So it's got, so this is the polarizability. So basically 3000 is the carbon hydrogen stretch. That's the vibration of the, so each of these, if you haven't done organic or something, each of these corner things is a carbon, and it's got 4 bonds to it. So if one's taken, the other 3 are hydrogen. So that's like a simple way to draw it. And there's a carbon here with 3, so there's a hydrogen stick in there. It's a hydrogen stick in there. So the Raman's going to be mostly sensitive to this carbon-carbon bond, I think, because that's not as polar as this carbon-carbon bond's polar. This one's not as much polar, but since it's around, so the carbon hydrogen is going to be like down here. So maybe that's 1600 thing, or maybe this spike over here, carbon bonds. But this thing with the 2 peaks in it is hydrogen carbon. So and there's 2 kinds of see those 2 peaks. There's kind of there's 2 hydrogens. There's 3 hydrogens here. And there's 1 hydrogen there. There's 2 hydrogens here and one hydrogen here, carbon hydrogen. So the OH is this big blob over here, and that's polar, so it's small in Raman because it's a polar group, so you shouldn't even see anything here. Like when you go to IR, that thing is huge. So this again is transmission, so it's upside down. So the water is there, and then these are the hydrogens, carbon hydrogens. Right. So it's kind of like in Raman, I guess you're kind of expecting one. I would expect from this like 1 peak from that carbon-carbon, but it's got a pretty big spectrum. So there's some component of polarizability and polarity in this molecule for all the different bonds in it. You can see they're quantized, but they're not spikes. They have a breadth to them, right? Whereas if you look at NMR, they're spikes, like they're actual just straight lines. There's no real breadth to it. The reason that it seems to be breadth is because this peak is split. So the nuclear spin is split 2 atoms away. It'll split this is proton NMR, so hydrogen. So if you go 2 bonds away, everything 2 bonds away will split that hydrogen. So the 1 spike that you have will be split. And then depending on how many that one's split by 2 bonds away, it'll split that one again. So you get split on top of split. That's why the 1 spike becomes split. So in an NMR pattern, you get from that molecule, you can actually generate this pattern directly. Like you can say what this pattern, every part of this pattern you can generate from that. There's no question. It's like 1-to-1, right? And then this is a carbon you can look at the hydrogens or you can look at the carbons. So it's carbon 13 NMR. And that's kind of much simpler because there isn't as much carbon coupling in it, so they aren't split as much. But they are just single spikes, right? So that's really a quantized transition, just like boom, nuclear spin, the radio wave, it absorbs it, and it only absorbs at one frequency, right? It's totally quantized, it's just a spike. Whereas the IR and the beryllium are going to be these kind of broader things, especially the OH group in this usually is really broad and really big. It's like water. If you look at water, it would just be a gigantic blob over here, right? Or if you look at silica with some water absorbed to it, you'll get some spikes and there'll be a giant blob, and the more water you have, the bigger the blob. So the amplitude of this thing is the amount of the stuff. So you can quantify, at least you can quantify relative to the other peaks. So if you know, say it was SiO2, you know how much, so you want to know how much water per SiO2, say you have nanoparticles of different size, and the water all goes to the surface. There's no water inside the SiO2 crystal or quartz crystal, or if it's glass. So basically, anyway, you can figure out the size of the particle from that if you want. Like figure out the surface area, figure out the percent of the silanes on the surface that have hydroxyls on them. Take an area of the OH peak, take the area of the SI peak, SiO vibration or something, and then from the ratio of those two, you can figure out how much surface area, because the OH is only on the surface, and you can figure out the surface coverage, like how much is that silica absorb water. Say it's like a desiccant in a thing of pills or something. You could tell, like from the IR pattern, you could tell if it's still a good desiccant or if we should throw it away, for instance, right? Because you could tell how much of the surface hydroxyl sites have been taken. Anyway, so it's useful. It's like fingerprinting, and there's no other way to get that. Like there's no other way to get those kind of numbers, right? So this is kind of useful, and it's pretty simple. Like just shoot the beam through, have an interferometer. It does the Fourier transform for you, it spits out the pattern. That's it. And then you just can do area things with it. This is for that same stuff. So the reason to talk about this, and this is the other thing, is mass spec, which is like take your stuff and then usually, let's see, I'm used to doing this in polymer. So polymers, you usually break it apart. But this stuff, so you just feed this stuff through in a solvent and then just vaporize the solvent. And then the molecular weights of the components depend on so it's going to be you ionize the molecules, they're going to flow through a magnetic field, they're going to go in a curved path. And then the ones where they fly off is kind of where these peaks show up. And that has to do with the charge versus the mass ratio. So you vaporize the stuff, charge it, put it through a electrostatic field, like a high voltage electrostatic, charge the molecules. Then as they fly through, if you have a magnetic path with a curved magnetic field, and you have a detector along the edge that'll pick up ions, then you can, this is basically going along that edge with the detector and saying like what shows up. UC has a really big mass spec center in the chemistry department. Like it's a whole floor over there. So this guy, I think Pat Limbaugh is now director of research or something at UC. I think it was his lab that he came here and set up that big lab. So there's a lot of mass spec here. Mass spec's pretty useful. From that, like if you have your metals or you have some ceramic like a rock or silica, so you can't do this with it, you have to take it and put it into HF, which one drop will kill you. Basically, you put it into this Teflon thing with HF, and then you put that into a microwave and cook it for like a long time. Then you take it out, and then you've dissolved the rock into whatever. And then you can take that stuff, you take like one small, it only takes a really small amount of material here, so you take like a fraction of a drop of that stuff, put it into a solvent like propanol or something, and then it vaporizes, does the same trick with it. But then you get like the pieces of the stuff you put in. So you can tell like if it was like gold deposited onto silica for a catalyst, you can tell how much gold, how much silica, that kind of business. You can also do that in a TEM or SEM, right, with the EDAX composition. But mass spec is one of the tools that people use. It's nice they have all the techniques here. The Raman's got kind of one big peak, which is this carbon hydrogen. So I guess that's what, what, I think that's what he's seeing here, like the one big kind of lump here. It's probably, if you deconvolute, so if you Fourier transform from the peak over to the right or from the peak over to the left, then you'll get this pattern. Like this will come out of it. So the same thing will come out of this curve. You just Fourier transform that, right? So if it's a Raman spec, Raman would be way out at the end. So these spikes would be separated by a lot more. Anyway, so maybe I can go through question one so long I don't have to answer question two. So question two is like the nightmare question. So one of the 2 or 3 nightmare questions. So this is the contrast. So this is kind of standard in scattering business. You talk about the scattering length versus the solid angle that you scatter it into. Anyway, this is just the contrast kind of, right? You're picking up a signal from these materials, and they're going to be he's saying they depend on these 2 terms, right? So like none of the other books or anything say like 2 terms. So the question is like, what is he talking about here? So now you can't get the book 13. Maybe you can get it, but I can't find it. So there's some other books, but none of those books talk about this equation. So then the question is like, what is he talking about? And this is a review. It's supposed to be like so kind of simple, basic. So susceptibility, so this is electrical susceptibility. So it's like how much, if you put on electric field on a material, how polarized does it get? So it's polarized per electric field. It's like a ratio itself. It's a derivative ratio between the amount of polarization versus the electric field that you applied. So Raman scattering, Brilliant, you're looking at polarizability. So basically, because the scattering event, so susceptibility is the electrical susceptibility to how much you get out of how much signal you're going to get out of it, right? So how much polarizability, then polarizability can be plus minus, it has to be squared. Which you can, so basically the signal is going to be the kind of the magnitude of that, so it's squared here. It's not going to have a phase to it. So when you square it, you get rid of the phase. So basically the plus minus part disappears, you just get the magnitude of it. So that's because the density fluctuations are a wave. So the acoustic vibration you're putting into it is a wave. And it's going to make the susceptibility will go up and down the opposite, right? So if you took an average, you get 0. So you have to square it to get the signal you're going to get out is going to be the magnitude of that. So it's how much it polarizes it with respect to density fluctuations. That's going to be your contrast kind of in this thing, more or less, right? So then why is it like adiabatic, so constant entropy, and why is it isobaric, constant pressure? Like, why is this equation written like that? And then the next question is, why do you have the adiabatic compressibility here, and why do you have the heat capacity here for the prefactors of these things? All right, so that becomes so I guess kind of you can say why it's this d chi d rho, and that's going to give you the signal that you get, like this intensity over here. But what about these prefactors? Like, where is that coming from? So, and I don't know, like no place really says, right? So, and he doesn't say either. He just says, here's this equation, it's from 13. You can't find the book 13. I guess he does say something here. I didn't read that. First term corresponds to proving a density fluctuation as constant entropy related to doublet Brillouin shifts by sound waves. That helps. Second term corresponds to non-propagating entropy fluctuations at constant pressure related to the Rayleigh peak. Let me see. So the Rayleigh peak is this central spike, the coherent, the elastic signal. Anyway, so this thing's set up like this. That kind of says something about it, I guess. I didn't actually read that this round. Anyway, so he's got, let me see if I can copy this thing down. useful. D sigma D omega. That's the compressibility. Rho squared kind of removes the units. D chi D rho squared at constant S plus T rho CP D chi D rho squared constant P. Right, that's that thing. So that's not bad. All right, so anyway, so we got this thing, right? So then you can say like so he's got constant S and constant P. That makes you think like DH is VDP TDS. At least that's what it makes me think. Right, so if you do DH dt, why did I do DH dt? I guess I said DH dt. Oh, I know why I said DH dt. Right, so then you have this is a constant S to get rid of that term, then that would give you that thing. That thing with a constant S, and then this at P would make this term go away, and that would be DH dt at constant P. Right. So anyway, which is like CP, right? So that's kind of like the second term of this with the CP has something to do with that. And then there's this one, right? So this one, that one is and I'll try to say why it's DH dt some other time, but basically you can get how CP is related to the BS, which is compressibility dV dP at constant S, which is something you don't usually see. Right? I mean, you don't usually have an adiabatic compressibility. That's what he has here. We have dP dt at constant S. So if you use this thing called the triple product rule. It's hard to recreate. That's called the triple product rule. Right. So here, if we say dPd, you can also say that dP dt. So dt dP at constant S, dt dP constant S, dP S, same as dV ds at constant P. That's a Maxwell relation. Right? So it's a horseshoe thing. So some reason I said dVds at constant P was easier to do this with. Probably you could do the same thing with this one, but anyway, so if you say dV ds at constant P, and then it's going to be ds dP at constant V, and then this one's going to be dP and x is dV at constant S, right? So this guy is the same thing. It's 1 over that guy, dV dP at S. So that's 1 over beta S. So this term has the 1 over beta S, and this term has a CP. So you have beta S and 1 over CP. So it's kind of related to this DH dt. But somehow the enthalpy, this thing has to do with the enthalpy. It has to do with the change in enthalpy with temperature. That's as far as I've gotten with this thing. I mean,
which thing has to do with the change in enthalpy?
All right, because these two terms are going to give you CP and 1 over beta S, right? So 1 over beta S, 1 over that is beta S, and 1 over CP is 1 over CP. So those two terms come from DHDT, the breakup of DHDT. So somehow this thing has to do with the enthalpy change with temperature to get this thing. That's what I got. I guess I could have done this DHD row or something and broken it down, but it's got something to do with this. I guess if I swap out temperature for density or something, maybe I can get the same answers that I get. Now you need temperature to get heat capacity. To get CP, you need temperature in this, right? And then he's got the T here. There's a T there, right? So that T comes from that T. And then anyway, so the T and the T are kind of coupled up. Anyway, I think it kind of works out that you can say something about that. I'm not sure how you're going to answer this. That's what I've got for it so far. Or you might find it someplace else in a book or something, but I haven't been able to find it. So that one is kind of out there for grabs, I think. That's as far as I got on it. So all right, so equation 2, differential equation. So there's some relationship with the HDT at these two terms to give the prefactors for what he got there. You know what else? This part, I mean, just that thing squared makes sense. Like that's like if you have a wave of density going through, that's going to be the intensity that comes out. But why? So this thing proportional to that alone makes sense. But then why S and P? All right, there's another part to this. The intensity is related to the enthalpy, to the kind of the change in free energy, I guess. So, like when you measure the I0 angle intensity, like the Rayleigh peak, I guess, that's proportional to the 1 over the thermal compressibility, which is a derivative of the free energy.
Is it the Rayleigh peak? So at 0 angle, it's like resolvability. Like
the scattering, yeah. So in this case, the Rayleigh peak is the intensity of the beam. But if you took the scattering part, so there's the intensity of the main beam that's coming through, and there's these inelastic parts. No, he's at an angle. So this is actually a scattered beam. Yes, that's a scattered beam. So in other words, he's shooting the beam in, and he's picking up at 90 degrees. So there's no main beam anymore. It's just whatever comes out. So the Rayleigh part means you came in with a certain frequency, and then so you polarizing the electrons within the bond. Then because they're polarizing and vibrating, they generate. So because of Maxwell's law, you have a magnetic field makes an electric field, so once you have the electrons vibrating, they're going to make a light. They're going to make light of that frequency because they're making a magnetic field when the electrons move. And then when those electrons move, they make a magnetic field, so it begins an oscillation. It's like dropping a rock into a pond. So once you have oscillating electrons, you have light coming off. It just comes off. It makes like dropping a rock in a pond. It makes waves coming off. So basically, the Rayleigh peak is the frequency that you put in comes out. There's no elastic loss in the process. You go in, you shake the thing, it's making noise kind of, or light, like coming off in all directions, isotropically, right? So, and it's basically that wavelength, whatever you put in. And then there's also the fact that the bond itself was already vibrating before you went in, so it's going to dump that energy into the light that comes off. It's going to shift it to a higher frequency. That's the anti-Stokes. Or the light came in and the bond absorbed some of that energy, and then it's going to shift it to a lower frequency, and then that's the Stokes line, which should be brighter than the anti-Stokes because taking it away is easier than giving it up. Or giving, yeah. So basically, it should be absorbing. The Stokes should be larger than the anti-Stokes. Anyway, so it's pretty complicated. So this Rayleigh peak is proportional to 1 over the thermal compressibility. And the thermal compressibility is a D change in the free energy with respect to pressure, I guess. So there already is some kind of enthalpy thing having to do with the intensity. He doesn't say where this comes from. And I can't find that book where it says it. So basically, we're on our own trying to figure out what this means. But there is some reason to think it would be at least free energy, derivative of free energy related to this. And the thermal compressibility is directly 1 over thermal compressibility is supposed to be the intensity. Here he's got isothermal compressibility at constant entropy. So this and that term seem to be directly related to DHDT, as far as I can see. So there's a couple different rabbit holes you can chase down this if you want. If you kind of give up, it's fine, but just say something. Just say like could be related to this, could be related to that. It's good enough. Like just kind of look at it and see what you can think about. If you can find the answer in a book or something, that'll be kind of useful. Like if you can find reference 13, just like haze and something.
Just find where the equation comes from.
Yeah, like what does it mean even, you know? Scattering of light by crystals. I have 3 books, none of them have that equation in it. Right. He puts it equation 1, like what is this? This 1978 Dover Publishing, so that's a paperback book. I might have this book, Scattering of Light from Crystals. I have to look at my bookshelf. I might have that book lying there because it's a paperback. Dover's paperback publisher. Anyway, so that's that thing. Other than that, I'm not saying anything about question B, unless you have questions. But figure 3 superimposes brilliant Raman peroxide. What is the difference in measurement technique? The difference, there is no difference, essentially, except that you need to have a different interferometer because you go into lower frequencies. So the interferometer is going to be different. And otherwise, it's going to be similar. Like the 2 techniques are going to be pretty similar. And you'll see, if you go to see Nichols' thing, you'll see it's basically an optic bench thing. And then what's the difference? The difference is in the mechanism of absorption. Basically, one's a bond vibration, and the other is lattice vibration, more or less. Right? Although he's doing beryllium for liquids, and he's doing it for drugs and things. So generally, though, you're talking about vibrations of the lattice. So for Nichols, he's looking at vibrations of a membrane, like how does a membrane move when it's subjected to acoustic waves. So you can get the modulus, things like that, right, for the membrane, which is kind of useful. How can phonon density of states be obtained from the spectra? So it's directly going to be so you're measuring. You're kind of already measuring the thing is kind of measuring the phonon. It's giving you the amount of stuff. So the intensity is related to the amount of stuff, and the frequency is the energy. So it's kind of giving you more or less the density of states. Like the amount versus frequency would be the density of states. So it's kind of more or less giving it to you. You have to translate what a longitudinal acoustic whatever versus a transverse acoustic means in terms of the amount of material, right? In terms of moles, but basically it's giving you the density of states. That's kind of what it's giving you.
That's the number of modes per frequency.
Right. Or and the frequency is the energy. It's like how if you throw an energy into a material, how does it distribute that energy into frequencies? It's going to vibrate. So if I have a bell and I blow up a bomb next to it, and then it's going to ring, right? So it took the energy from the bomb and it converted it to whatever it rings. And the density of states, and if it was a monotonic bell, it would be just one spike. If it was a collection of bells, it would be a spike for each bell. If it was a real bell, it would have a bunch of spikes for the overtones and things, different parts of the shape of it.
Okay.
So it's going to have some complex way it distributes the energy that's given to it. Thermal energy is just like kind of all the spectra, right? So anyway, so equation 4. All right, so let me get down here. Equation 4 is like at the end here. So all right, so where is it? Oh, all right, we're almost there. Almost there by spooling.
Yeah,
Oh, that's it. All right. Yeah, so this is just so Bragg's. All right, so we got. Let me write this down. B equals lambda nu B over 2n sine theta by 2, and this is velocity of sound, and that's the frequency, right? So we've got so we have Bragg's law, like d is lambda by 2 sine theta, and if you're doing scattering, you call it theta by 2. So basically, you're going to come in, and there's a series of planes, and it's going to come off. So if you talk about theta for XRD, right? But if you look at it from the perspective of the plane, it's a specular reflection. So this is theta, and this is theta. So this guy becomes like theta by 2. Or this, let's see, if it's diffraction, let's see, I got this backwards. Let me do this cleaner too. So we're gonna go off there, and the plane has to be like it's called a specular, means mirror. So it has to be like a mirror. So this angle has to equal that angle. But and then that means that this also has to be that angle. So this thing has to be 2 theta. That's diffraction, right? That's XRD. You plot XRD, you do intensity versus 2 theta, you see a bunch of spikes. Right? They say it's FCC. So the 2 theta comes because you have this reflection plane, and you say that's 1 theta, that's 2 theta. It's like a mirror. So you shine in, you get the reflect, even though it's not, it's happening because this guy goes here, this guy goes to that plane, and these two are given off this kind of rock thing, and you see, like, if you draw the circles right, you'll see an interference pattern shows up at that angle. Right? If you do the rock thing and they have a peak for every wavelength of the light coming off, you'll find out they constructively interfere just at that angle. Right? So basically, it's a coincidence that it looks like a mirror. It's not really specular. So anyway, so this is called, that's called either 2 theta, or in scattering, this whole thing's called theta. So if you write Bragg's law for diffraction, it's theta XRD. So lambda by 2 sine theta XRD. If you do it for light, it's like theta by 2, because they call it the whole angle theta. For whatever reason, some guy at the beginning did it that way, and the other guys did it the other way. And they both call it theta, so it's confusing, right? So, but anyway, theta by 2 means you're doing light scattering, and if it's theta, then it's XRD, or wax. Sometimes they call it wide angle X-ray scattering. And if you're doing X-ray scattering, small angle X-ray scattering, goes to light scattering, it's theta by 2. So anyway, in this case, he's got theta by 2. That means he's like, that's like a light scattering imprint. And also the n, that's how many, if you put in a grid and you shoot light through it, you get like a series of peaks from 1D spacing. So that's like N1, N2, right? So those are the orders of the reflection, right? N3. So you can get more higher order reflections if you want. Usually in diffraction scattering, you just consider n as 1, because you don't get to see those. They're off at higher angles or something. Anyway, that's the wavelength. So this is just, that's like the D spacing. That whole thing is the D spacing. Or it's kind of generally like R, like some distance. Like the probe distance that you're looking at. So you shoot light into something that isn't a crystal, there's no D spacing, but there's still, if you pick up scattered light at some angle theta, then at theta by 2, there is some kind of interference pattern, right? That of things that are separated by this R, which is D, right? Which, if you have a liquid, so if this is a diffraction from a crystal, if I have a liquid, I get a big hump because the liquid atoms have a certain kind of average spacing that they like to be at. That's the middle of the hump, and a lot of them are just around that. So it's a broad hump. You get all the distribution of different sizes from that. Anyway, so basically in scattering, you're dealing with these kind of hump things. So you talk about this R instead of D, but basically it's Bragg's law. It's the same thing. So you call that R. So there's some size scale R. So you have the velocity of sound is a frequency times R. Velocity frequency is like 1 over time, and this is like distance. So you get velocity from that. That tells you the sound velocity through the material. So the frequency of absorption, so in other words, the energy of absorption, or H nu, then the energy of absorption is related to the velocity of sound going through it. And the sound going through it has a certain energy that's related to the frequency of it traveling through it. So basically that thing, the velocity is like an energy, the frequency is an energy. To convert between the two, you need this kind of de-spacing that gave rise to the scattering. Scattering is like just throwing rods into this system and saying like, do the two ends of the rod fall in the phase? Right? So if the things, okay, so that's just converting. That's the size scale of the system, is that R, and then times the frequency gives the velocity. That one should be kind of straightforward, I guess, unless. And the other one isn't that straightforward. So that's that thing. And then this thing is like, so the attenuation, meaning the intensity of so attenuation means the spikes in the Raman. So like here it's the intensity, right? So the amplitude of the intensity. So attenuation means you're looking at, if you are looking at IR, so it attenuates, it drops the intensity. But if you're looking at transmission, it would, or this is transmission, and if you're looking at absorption, it would be a spike. So attenuation is the spike number. Like how much does it spike? What's the peak value of this thing? Anyway, it's a spike for it. You can do either one either way. So you can plot, this is attenuation being plotted, right? And then this thing, let's see, the IR is being plotted as transmittance. Okay, so there, let's see, let me go back over here. So you have what we're using a pile of paper. So we have this written down somewhere here. So so you say like the intensity that I measure is the intensity I put down, I put in, and then there's e to the minus attenuation. This is linear absorption or attenuation. So the units of this are going to be kind of change per distance, or 1 over distance, and then times the path length through the sample, and then times how much concentration you have. So it's the units of this thing going to be like 1 over distance concentration, right? It's how much it absorbs the light per distance per concentration. Because if you double the distance, you get twice the absorption. Double the concentration, you get twice the absorption. Right, so that's Beer's law, which comes from the I equals, how do you do this again? I equals, the change in I equals I times, so the change in I is negative at absorbed, times this absorption coefficient times L times C. Then you get di over I here. If you integrate that, or it's dl, change in light. You integrate the dl, and you get alpha CL, because it's 0 to L here, and here it's I0 to I. You get ln of I over I0 equals alpha CL negative. So that gives you back this equation. So it's called linear absorption because the change in intensity is proportional to intensity linearly, and the coefficient. So if you have twice as bright, you get twice the change. Half as bright, half the change. That's a linear relationship between the intensity, and then you get this exponential function for linear absorption. So linear absorption, it's an exponential function, exponential decay. In concentration, this is constant, right? So anyway, so what does that give you? So he says alpha equals pi gamma over velocity of sound.
So meters per second, and gamma is full width at half max of the Raman peak. So he's got his Raman peak. This is the peak height, and then there's this full width at half max number. So this we got that the velocity of sound is basically the d spacing, or this r number times the frequency, right? So then and the full width at half max, the x-axis on this is frequency, right? So it's kind of like intensity versus frequency. So basically, this full width at half max is also frequency. It's also that's a frequency number, and this is distance per frequency. That's also frequency. So the units will work out here. This alpha should be 1 over distance. 1 over distance in concentration. Basically, usually it's like the linear absorption coefficient is 1 over distance. So basically the velocity is meters per second, or it's the spacing size for the event times the frequency, and frequency and the half width, full width and half max is also frequency. So that will give you 1 over distance, which is what you want for units. So the units work out. That's good. It's an equation that the units work out. That means that's handy. Because you get up with 1 over size, it's alpha times distance gives you this argument, like without c is just alpha times, usually alpha is in inverse distance. Like it's a pure compound, c's 1, I guess is what it's for. So anyway, so you have that the units work out, that's good. And then you have to just say that this frequency thing, so the broader it is, the more absorption. In other words, if it's narrower, I get less absorption. If it's broader, I get more absorption. Right? So it makes sense that the absorption would go with the breadth. But if I have a peak of the same breadth at a higher frequency, then the delta frequency for the same shaped curve, I would get a smaller, if it's a higher frequency, I would get a smaller breadth for it. I guess is the way this works. So you have to, this is like a normalized the frequency divided by where the absorption is gives you a normalized breadth, a unitless breadth. It's like a unitless breadth for the peak. So it makes a peak at a different frequency comparable to the other frequency. So it's kind of normalizing the breadth to give you the now why it doesn't include like the actual intensity absorption, I don't know. Basically, I guess the intensity of the absorption is going to be like the concentration. So it's going to be the breadth. So the intensity, so it's going to be the absorption coefficient times whatever the real concentration is. So that concentration, the height of it is going to be like, if you double the amount, it would be twice as high, but the breadth would be the same somehow. So anyway, however you want to argue it, that's how I argue it. I end there. But I mean, again, this isn't in the books, you know. There isn't a book that says like this is the answer to this thing. So, but that's the way I see it for that thing. And what else is in there? All right, it just gets harder here after that. This is the high point. Figure 16, right? So I kind of already mentioned this figure 16. So there's a lot of this, there aren't answers, like discrete answers to these things. There's wrong things you can say, but there's not exactly the right thing to say. You might find the right thing. That would be great. I'll give you some extra points, but basically saying the wrong thing wouldn't be good, you know? So this is like this thing about the drug. And then he's got longitude, amplitude, because the glass or the liquid won't have a transverse amplitude, so he's comparing the longitude amplitude shift for the crystal. And then it goes through this glass transition. So above that temperature, it's a liquid. So you only have longitude for the liquid. And then there's, so he talks quite a bit about this pattern. He says something about it. And then I think I don't know if I dug up this paper or what, 95 Newtonian scattering technique for investigating acoustic and optoacoustic properties. Application to polymers. No, I don't have that paper.
For some reason, I stuffed in this other paper here. This is from it's like an old homework, you know, so. For some reason, I stuffed in this Claythwaite density functional theory, IR Raman. I think because someone was interested in density functional theory last year. So I put that in. So forget about that paper. I don't have the paper that you need. And I'll put in those two other books. But basically, this is just kind of a hand waving thing. Let's see, this shows it depends on brilliant frequency shift and the full width at half max for the peaks of the function of temperature for an organic drug that becomes glass or a crystal. Why do the curves differ for the glass and the crystal? I mean, I think it's you can just say that the modulus, the strength of the bonds is higher in the crystal than the glass. You expect a higher energy or frequency absorption for the crystal than the glass. That part's, I guess, kind of straightforward. The glass isn't bonded together. Then when you get to the liquid, it drops even further. So that's like liquid down here. Why the crystal and liquid? So that this is that's the TG. So that if there's a shift there because the crystal isn't pure crystal, it's got some glass in it. It's like some of it couldn't crystallize, so it's a glass, and then it reaches TG, and there's still some drop after that. So both of them show a little drop there. I'm not sure what this shift thing is here. And then the big question is this half width at half max business. The crystal's got a higher one than the glass, which means that or you can see that the crystal has a broader peak than the glass at the bottom. Right, so and apparently that has to do with this absorption coefficient. So the crystal's absorbing more than the glass, according to his equation 4, whatever it is, 4 or 5. So this really looks reminiscent of something to me, like in I can't place exactly where this is coming from, but that the disordered stuff has a sharper peak than the ordered stuff. Means something, but I don't remember exactly what. Anyway, so there is a meaning why that's broader than that. It definitely has to do with this. Will definitely have a higher absorption than that, but it might be just that you're spreading out more frequencies. Like somehow when they're bonded together, you can go over more kind of modes of vibration, spreads it out, something like that. Any answer is going to be good for this. There is a reason for the sharpness in when you go, Nichols would know this right off because he does this dynamic stuff all the time. But basically, there's a reason that it's sharper in the liquid than it is in a glass than it is in the crystal. Anyway, so whatever hand waving thing you can do for that's okay. And just something about drugs there. So that's about it. What are we doing for time? 4 minutes, good. I wanted to finish this off. So the glass stuff, I'm not going to say anything else about glass. There's no homework on that. And I just wanted to say this last thing is this thing. So the polymer heat capacity. So the guy in last week's homework, this Wunderlich guy is like a famous, I think he's dead, but basically, Steve Wunderlich, he wrote like so many papers in the 80s and earlier than that, like the 60s, about like polymer DSC, like glass transition, crystallinity, right? And then he's referenced in that other paper, and then he's here too. He was at Florida State. He spent his whole career there, and then he went to RPI at the end of his career in Albany. But anyway, then he had a bunch of students that went off and became professors too. So there's a couple of people floating around that are connected with him. Anyway, so it's kind of interesting though, because from our perspective now, we know a lot about Einstein and where you would use Einstein model, right? Because we have the aluminum thing, and that's a perfect little spring thing, right? And it's not interfered with the other modes. And then what Wunderlich did is like take just the Einstein model, then like say, well, that's going to work for polymers, and then just basically it works pretty good for polymers. You can just use the Einstein model for polymers. And then, so that's one way to do it. The other thing you can do is say, because it's a linear chain molecule, you don't have 3D if you use the Debye model, let's see, if you use the Debye model, then you're going to have, this is upside down. It should be t to the 3 up here. And then the Einstein thing and that to the 4. So there's something weird. This equation isn't right. But anyway, D3 is the Debye third order integral for 3 dimensions. So, I mean, one of the things they said was just use a one-dimensional Debye. So take this, like in the wiki page, they have a Debye integral function. You can do it for any n that you want. So you can do it for 1D. Then you have that equation, just plug that in to get the heat capacity for polymers.
Does it depend on the crystallinity of the polymer?
These are liquid. These are like in liquids, like amorphous polymer. Like they're doing polystyrene's the one they're using, it doesn't crystallize. It does, if you make it tactic, it can crystallize. Basically the kind that you have for a Scotch tape container, that's amorphous. Any polymer is clear is amorphous. And they're crystalline, they're like white, like a milk jug. Semi-crystalline anyway, but so yeah, it wouldn't matter if it's crystalline. That would have an effect. I mean, it would probably go back to just like a metal heat capacity for a crystal. But when it's amorphous, there's only correlations along the chain length, I guess. That's what they're talking about. So they use D1 instead of D3. Anyway, so you can calculate, so you can simplify that into a polynomial if you want. This Tazarov, so there's like a Russian guy that came up with a polynomial to talk about the heat capacities. You can talk about the different modes of vibration, sum them up, and you can predict the heat capacity as a function of temperature. For this for polystyrene, it's like a Scotch tape container, plastic. You know. So it's kind of interesting to mention that there are people that do heat capacity of polymers for a living. Although I don't think they're making a living at it anymore. This is in the 60s, so 60s to the 80s, and you can match it up basically with the same theory, like to take the metal stuff. And it's typical, like you're going to take the metal stuff and just plop it into polymer, like the Flory-Huggins equation, which we'll talk about next week. We'll go through some of the different modifications of the mixing equations. Anyway, so that's it for that. I'm not going to, there's some stuff about fragility of glasses and stuff in here, but I'm not sure it's worth going through. We don't have time to do it anyway, because I already spent 3 weeks on heat capacity, so just flush it out. He mentions at the end of the chapter some stuff, and there's more things in the slides about it, but I think we don't need to worry about that. So yeah, that's it. 250. Good. So we can pull that down. Huh?
That reference 13.
Yeah.
Every university except UC has it.
Is that right?
So I ordered it from Miami, but
It'll take a month.
you can rent it for an hour, or not rent, but loan it from archive.org in hour increments. You have to return it and then read.
Oh. Oh yeah, it's too bad you didn't give a page number on it.
I found it.
Oh, did you?
Yeah.
Okay.
It's equation 8.3.
I might have it, yeah. Now, someone last year, I think, did it. I can dig up though. I can just look in the old, I think on the Canvas, I can go back into the old homeworks, right? So I can dig up, if I can find it, I'll post it on the thing by the homework thing. So you can look at it, you know.
There's a whole bunch of other stuff along with that expression. Omega to the 4 times.
I mean, it seems pretty weird that it's the only book that has that equation in it, you know. And, yeah.
What's that? Yeah.
Right, so that could be bonus points. Look, there's something out there hanging, low hanging fruit. And he's willing to sell it to you.
I have it on loan right now, so nobody else can access it.
The $5 will go a long way. So I better stop the recording. The illegal graft will come up here.
The main paper. I was gonna try to email it. Yes, some weird email address.